So we have seen sets, now let's move on to relations. As we saw, a set is a collection of items and we can construct new sets from old sets. So we can take unions, combine two sets into one, we can take intersections, take the common elements, we can take the difference, that is take the elements of x which are not in y, and if we define the universe with respect to which we are working, we can define the complement, those elements that are not in x. Now in general we are interested in carving out subsets of a set, and so we use the set comprehension notation. So what this does is it takes a base set and takes elements of that set, then it applies some condition, those elements we are interested in, and then it collects them all together. So we can take all the integers which are divisible by 2 or not divisible by 2 in this case, so we get the odd ones, so those where the remainder is 1, or we can take all fractions in which the numerator and the denominator have no common divisor, or we can take, for instance, the real numbers which lie in an interval with the left closed interval 3 and the right open interval 17. So now we will see a new way to combine sets to form new sets, and this is called the Cartesian product. And in the Cartesian product, basically what we do is we take two sets and we take one element from each and form a pair. So A cross B, as it is called, is the set of all pairs which we write with this normal bracket notation A comma B, such that the first element A comes from the set capital A and the second element comes from the set capital B. So for instance, if A is the set 0, 1 and B is the set 2, 3, then all possible pairs we can form in the Cartesian product are 0 combined with 2, so 0, 2, 0, 3, and then 1 combined with 2, 1, 2 and 1, 3. So we have 4 possible pairs. Now in sets we said that the order of the elements is not important, but of course when we are doing this kind of a pairing, then we know that the left set comes from the left part of the product and the right element comes from the right part of the product. So for example, 0, 1 is not equal to 1, 0. So here we have to respect the order when we talk about a pair. Now if we have sets of numbers, right, then we normally visualize the product as a space which we draw familiarly as a graph. So for instance, if we take n cross n, then we draw n cross n as this grid where on the x-axis you have one copy of n, on the y-axis you have another copy of n. And for example, if you want to look at the pair 2, 3, then it says that the x-coordinate is 2 and the y-coordinate is 3 and you get this point. And similarly, if you look at the point 5, 6, you get this point, right? So you can take the first coordinate, plot it on the x-axis, take the second coordinate, plot it on the y-axis, and where those 2 points meet on the grid is the point that we are interested in. So this is one way of visualizing a binary relation on numbers, and we can do the same thing if we are using, say, the reals, in which case the grid points that we are going to plot will have real coordinates and not just natural number coordinates. So now we have this Cartesian product which consists of all possible pairs of the two sets, and as we did with set comprehension, we might want to pick out some of these sets, some of these pairs, and this is what we call a relation. So we combine this Cartesian product operation with set comprehension. So for instance, we can take all pairs of numbers which are natural numbers m comma n, but we want to insist that the second number is 1 plus the first number. So we get, for instance, 0, 1 because the second number 1 is 0 plus 1, 2, 3 because 3 is 2 plus 1, 17, 18 and so on. And if we plot these points alone on the right, then we get these. So we get a subset of the overall points, and these points satisfy this set comprehension condition. Another example would be pairs again of natural numbers d comma n, where d is a factor of n. Remember, d is a factor of n means that if I divide n by d, I get remainder 0. So for instance, 2 is a factor of 82, 14 is a factor of 56. So these will be points in our relation. So this is what is called a binary relation. So formally it is a subset of the product. So we take the Cartesian product, all possible pairs, and then we apply some kind of a condition which filters out the pairs of interest to us, and it gives us therefore a subset of pairs, and this is what we call a relation. Now to denote the pairs that belong to the relation, either we can give the name of the relation as a set and say that A comma B belongs to R, or sometimes to say that A is related to B, we use R as a kind of operator. We say A is related by R to B, and so we write A R B. So these are two notations which you might see in different books, and they mean exactly the same thing. So let's look at some other examples of relations outside the numbers. So supposing you have a school in which there are some teachers and some courses to be taught. So T is the set of teachers, C is the set of courses that are being offered in this term. then you need to describe which teachers are teaching which courses. So we would have an allocation relation A, which is a subset of all possible pairs T cross C. So every teacher in principle could be teaching every course, but of course this is not normally the case. We don't have all teachers teaching all courses. We have some teachers teaching some courses. So we would specifically say take every pair of possible teacher course pairs. Then we take out those where precisely the teacher T is actually teaching the course C, and we collect those together to form this allocation relation. So here is a different graphical way of describing a relation, not in terms of the grid and the graph that we have learned when we do graphs in school. So this is also called a graph, but this is a graph in which we have some nodes representing the elements of the set. So on the left hand side we have 5 teachers, on the right hand side we have 4 courses, and the arrows from the left hand side to the right hand side connect the pairs which are in the relation. So we see that Kumar teaches maths, Deb teaches history, and so on. So this is a useful way of visualizing relations on finite sets, and we will see this often as we go along. Another example of a similar type of a relation is that between a parent and a child. Specifically, let's look at mothers and children. So if we have a set of people in a country, then we can take the set of all pairs of people and then isolate from that pairs in which the first element of the pair is the mother of the second element. So we want M comma C, which belongs to P cross P, such that M is the mother of C. So let's go back to our numbers. So supposing we want to plot all points which are in R cross R, which are at a distance 5 from 0 comma 0, which is normally called the origin. So one thing you need to know for this, probably you should have learned this at some point, is that if I take a point A comma B and calculate its difference from 0 comma 0, so this is calculated using the Pythagoras theorem, and it comes out to be square root of A squared plus B squared. So in other words, the relation we are looking for in this case is all A comma B whose distance from 0 comma 0 is 5. So all A comma B in R cross R such that the square root of A squared plus B squared is equal to 5. So here are some of the points 0 comma 5. For instance, you can see 0 comma 5 is there because the sum is 0 plus 25 and the square root of that is 5. 3 comma 4 is there because 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, square root of 25 is again 5. So interestingly, these points, if we plot every such point in R cross R which satisfies this, actually defines a circle of radius 5 with center at 0 comma 0. So relations can define interesting geometric shapes, and very often we do deal with geometric shapes in this relational form because it's easier to manipulate than looking at pictures. Now depending on how we are going to view a relation, we can look at it in different ways. So remember that we looked at rationals in reduced form. So we said that a rational in reduced form has P comma Q, P by Q such that P and Q are integers and the GCD is 1. Right? That means that they don't have a greatest common divisor other than 1. But we can also think of this as a relation on integers itself. We want all pairs of integers. So every rational is really a pair of integers, the numerator and the denominator. And we want every pair of integers where the GCD is 1. That is, there is no common divisor. So we don't have to restrict ourselves to binary relations. The Cartesian product notation extends to multiple sets. Let's look at 3 sets. For instance, remember Pythagoras' theorem which says that the square on the hypotenuse is the sum of the squares on the opposite sides. So what values of A, B and C could be the sides of a right triangle are determined by Pythagoras' theorem. So we would say that A, B and C is a valid triple in the Pythagoras sense if A, B, C belongs to n cross n cross n. So here we now have 3 copies of n, and A, B, C must all be non-zero, they must all be positive lengths. We don't want to have triangles in which one side is collapsed to a point, and we want the constraint that A squared plus B squared is equal to C squared. Here is another example. Suppose we look at squares on the plane, squares with real corners, right? So a corner is a point x comma y which is in R cross R. So we define the x coordinate and the y coordinate that defines the corner of a square. And we want 4 corners which together form a square if we connect them by lines. So for instance, if you look on the right, the 4 blue dots correspond to a square which is cornered at 0, 0, 0, 2, 2, 0 and 2, 2. The red points also define a square, because this is a rotated square, but then if you rotate it vertically, you will turn out that this diamond is actually a square. So there are many such 4 sets of points which form the corners of squares, and we might be interested in all such 4 sets of points. So now we have a relation which involves 4 sets of points, but each point itself is a pair of real numbers. It's an x and a y. So square, if we think of it as a relation, is actually a relation on r squared, that is the first corner, times r squared the second corner, times r squared the third corner, and the fourth corner r squared again. So this is actually either a relation on 8 copies of r, or if you want to group it, 4 copies of pairs of r. So this just says that we can take relations on an arbitrary number of copies of a set, and we get larger and larger. From pairs we move to triples, we move to quadruples, and in general if we have n copies, we call this an n-tuple. So there are some special binary relations which pop up all over the place, so it's useful to know their names. The first one is called the identity relation, and as you would expect, the identity relation maps every element to itself. So if I take A cross A, so first of all the identity relation is defined on 2 copies of the same set, because identity means equality. So I take A cross A, so this has all kinds of pairs A comma B where both A and B belong to A, and now I want the condition that A is equal to B. So in other words, I want things of the form A comma A. So if I plot this, for instance, on the natural numbers n cross n, then I get 0, 0, 1, 1 and so on, and these are the points which are drawn on the right in this grid. Now a point of notation, it is tedious to write this notation as it is, as A comma B times in n. So we don't want to have to write out this long thing. So sometimes we simplify this by saying I want all pairs such that A comma A belongs to A cross A. So what we are really saying is that the second A and the first A must be the same. So we are collapsing the equality and this. Now this is not technically correct, but this is often used in order to simplify the notation. And sometimes we might drop the product altogether. We might just say we want all pairs A comma A where A comes from the set A. So in other words, we are pulling out 1 copy of the element from the set, and then we are constructing a pair by taking 2 copies of it. So all of these are equivalent ways of writing this, although only the first one technically follows the notation that we are using to introduce relations. Now there are some properties that relations may have. The first one is called reflexivity. So reflexivity refers to the fact that an element is related to itself. So a reflexive relation is one in which for every element A comma A belongs to R. So in other words, based on what we just wrote above, it means that the identity relation is included in R. So it doesn't mean that that's the only thing. The identity relation has only the reflexive elements. A relation that is reflexive will have the identity pairs and it will have other pairs, but it must have all the identity pairs to be called reflexive. A symmetric relation, for instance, is one where if A, B is there, then B, A must be there. So for instance, looking at reflexive relations, one example is the division relation. So if we make sure that the numbers are not 0, then we know it is reflexive because every number divides itself. So if we take the division relation as the relation that we introduced in the first part of this lecture, that would be reflexive because A divides A for every A which is not 0. Similarly, symmetric relations, if we look at pairs where the greatest common divisor is 1, in other words, they have no common divisors, this is what happens, for example, in reduced fractions, then it doesn't matter whether we write it as A comma B or B comma A. So if A comma B has greatest common divisor 1, so does B comma A. So A comma B and B comma A must both either be there in the relation or neither will be there. Similarly, if we look at this, which is asking about the absolute value. So it's saying give me all numbers A and B such that A minus B is either plus 2 or minus 2. So the absolute value takes the difference and removes the negative sign. Now we see that, for instance, if 5 comma 7 is there, then 7 comma 5 must be there because they both have the same difference depending on how we write it. Normally in subtraction we have a sign difference, but because we are taking the absolute value, there is no difference actually between these two. So this absolute value relation also, if we fix, is a symmetric relation. A third property that relations may have and which are useful is called transitivity. So transitivity says that if we have 2 pairs which are related such that they share an element, so A is related to B and B is related to C, then A must be related to C. So again, our divisibility is a relation. So supposing we say that 2 divides 6 and we say that 6 divides 36, then from this we can conclude that 2 divides 36 as well, right? Similarly, if we take less than, if we say that 3 is less than 10 and 10 is less than 28, then we know from this that 3 must be less than 28. So this is transitivity. So if we want to draw it pictorially, if we have 3 elements A, B and C, and this arrow, remember we had this graph notation which says A is related to B and B is related to A, then this dashed line represents the requirement for transitivity. A must be related to C. Now we saw symmetry. So symmetry says that if AB is in R, then B comma A must also be in R. Anti-symmetry says something different. It says if AB is in R, then B comma A should not be in R. So less than, for example, which was transitive above, is also anti-symmetric. If we take strictly less than, if A is strictly less than B, then it cannot be that B is strictly less than A. So this is an anti-symmetric relation. But anti-symmetry doesn't require that one of the two must be there. It only says that if one pair is there, the opposite pair should not be there. Okay. Similarly, if we look at our mother and children example, obviously if P is the mother of C, then C cannot be the mother of P. Okay. Now there may be P and C such that neither P is the mother of C nor is C the mother of P. So that is allowed. We don't insist that every pair P comma C must be related one way or another, but if it is related one way, it should not be related the other way, is what anti-symmetry says. So if we combine some of these conditions, we get an interesting class of relations called equivalence relations. So equivalence relation is something that is reflective, reflexive, symmetric and transitive. So as an example, supposing we connect together all numbers which have the same remainder modulo 5. So for instance, 7 has a remainder 2 with respect to 5 and so does 22. So 7 and 5 would be related in this way if we define the relationship as having the same remainder modulo 5. Now notice that if two numbers have the same remainder modulo 5, that means that going from one number to the other, you are going in multiples of 5. So for instance, 22 minus 7 is 15. Right? So this is this modulo arithmetic. So if you add the number that you are dividing by, then you get the same remainder. And so in set notation, we can say that the integers modulo 5 are all pairs A, B, such that B minus A mod 5 is 0. In other words, we are not asking what is the actual remainder of B and A. We are just saying that B and A are separated by a multiple of 5. Therefore, they must have the same remainder modulo 5. Now this divides the integers into 5 groups based on the remainder. So there are the group of numbers which are divisible by 5, they have remainder 0. Those like 6, 11 and all which have remainder 1, 7, 12 and all which have remainder 2 and so on. So we have 5 possible remainders 0, 1, 2, 3, 4 and therefore this divides the set of integers into 5 disjoint classes. Now, as an example of modulo arithmetic that we are all familiar with, consider what happens when we look at a normal clock. Now a normal clock measures time from 0 to 12 and then cycles around again. So though there are 24 hours in the day, the clock is actually partitioning these 24 into 2 sets where we have 0 and 12 as same, 1 and 13 as same and so on. Right? So 2 AM and 2 PM, there is no distinction on the clock. So the clock is actually showing us this equivalence class of hours regarding AM and PM as being equal, and we have to know from context whether the clock is showing AM or PM. So the main thing to note about an equivalence relation is that it partitions a set. It partitions a set into disjoint groups. All of the elements within a group are equivalent and all of the elements outside across groups are not equivalent to each other. So the groups of equivalent elements that we form through an equivalence relation are called equivalence classes. So this might look a little abstract now, but equivalence classes really represent a kind of equality, and sometimes we are happy to work with this equality in terms of equivalence relations rather than actual equality, and it has very much the same properties as equality does. So to summarize, as we have seen, a Cartesian product can generate n tuples of elements from n sets. So if we have x1, x2 up to xn, n sets, these can be different or the same. Then we can take one element from each set and form an n tuple small x1, small x2 up to small xn. And when we now pick out some particular subset of these n tuples, we get a relation. So for instance, if we take pairs from n cross r and we want the second element of the pair, the real number, to be the square root of the first element, then we get m cross r such that r is square root of m. So here on the right, we have seen, we show one picture of this. So there are some elements like 2 comma square root of 2, 4 comma 2, 1, 7 comma square root of 7 and so on. Now just notice that in this picture, the y-axis is elongated compared to the x-axis. So this is not in some sense to scale in both dimensions, because the square root function behaves like this. So we have seen that there are some properties that we would like to record of binary relations: reflexivity, symmetry, transitivity, and sometimes anti-symmetry. And using reflexivity, symmetry and transitivity together, we get what is called an equivalence relation. And equivalence relations partition sets into equivalence classes which behave like equality. Thank you.